Hey everybody, this is Mr. Piercy, and what we're going to be looking at today, this is the first part of a pair of lessons or a pair of videos that we're going to be making demonstrating the very kind of origins of geometry. Every year at the beginning of the school year, I always ask my geometry students, what do you think you'll be studying in high school geometry this year? And inevitably, all they say is, well, we're going to be studying shapes and stuff, meaning that they're kind of relying on prior knowledge, things that they've done in previous math classes where they were identifying, different types of triangles, acute, right, scalene, isosceles, equilateral, different kinds of quadrilaterals, squares, rectangles, rhombuses, and three-dimensional shapes like pyramids and prisms. Well, they think that they're going to be using a lot of that stuff. Well, the analogy that I like to use when describing what students already know about geometry is with that of an iceberg, meaning that everything that they know about already in geometry is really just the tip of the iceberg. And what we study in high school geometry is really all of the stuff that's hidden beneath the surface of the water. All of the stuff that's underneath the water that makes up the majority of the iceberg. That's really what high school geometry is about. Uh, so if you happen to have the handout associated with this lesson, or if you're just kind of following along, that's fine. But I've added a little bit of extra stuff here. What we already know about in geometry, what we typically refer to as geometry, is really known as Euclidean geometry because there's a mathematician way back when, like around somewhere around 300 or 350 BC, is when the time that Euclid lived, and he developed the system that we generally think of as geometry. So all of the shapes that we know, circles and squares and pyramids and all that stuff, it's all based off of what we know about in Euclidean geometry. I've included other types of geometry. There have been other types of geometry that have been developed recently. Euclidean geometry stood pretty much unchallenged for about 2,000 years. Um, what we see here, this is spherical. This is spherical geometry, and it has some unique characteristics, meaning like most people will understand that the three angles of a triangle typically add up to be 180 degrees. Well, in spherical geometry, you could have angles where all three angles of a triangle are 90 degrees. So clearly it would be larger than 180. There's also what most people think of, like if I kind of do like this and then do like this, that in spherical geometry is a polygon. So the smallest sides, or the fewest number of sides that a polygon can have in Euclidean geometry is 3, meaning it's a triangle. Well, I can have uh, a two-sided polygon in spherical geometry, and this is, I believe, known as a lune, kind of like the crescent moon, like a loon or luna, something like that. Well, the next one that we see here, this is hyperbolic geometry. A lot of times visually it's represented by a shape that looks like a Pringles potato chip or the shape of a saddle. It's possible to have um, different things about it as what we currently know in Euclidean geometry. Again, the analogy is that triangles can have, the three angles of a triangle can have a sum where all three angles are less than 180 degrees. The circumference of a circle can be greater than what 2 pi r is typically in Euclidean geometry. The shortest distance between two lines is not necessarily, or between 2 points is not necessarily a straight line, but a curved line. And here, this last one, I don't really care too much for it personally, because it's not really a fully developed geometry as far as I know, but we refer to it as a taxicab geometry, where imagine like you're looking at an overview, like a above ground view of a big city like New York or Los Angeles, where a lot of their city is outlined on a grid like this. Well, let me pick another color here because the green's not going to show up super well. Let's try and pick orange. We'll try orange. What we see here with the green line, the green line is what we would represent in Euclidean geometry as the shortest distance between 2 points is a straight line. Well, in a city, like if we were actually driving through a city, I can't drive along that green line. I would have to drive along the city streets where I would, I could come up here and then come this way and get to the same spot in the same amount of time. The difference between Euclidean geometry, the shortest distance between any 2 points is a single straight line that connects them. Well, in taxicab geometry, there's multiple ways that I could develop the shortest distance between 2 points, and the red line, the blue line, and the yellow line, or paths I should say, those are all ways to represent the shortest distance between any 2 points in taxicab geometry. Well, moving on, so there's lots of different kinds of geometry. The one that we primarily think of as geometry is really known as Euclidean geometry. What you guys as geometry students really need to understand is that the very foundation, the very, very beginning of what geometry really is, comes from 3 terms that are known as undefined terms. There's only 3 undefined terms in all of geometry. They are a point, a line, and a plane. And from those 3 things, we're able to create, or rather Euclid and his colleagues were able to create a system of math known as geometry that has just so much about it. Like I said, what we know right now in geometry coming into high school is just the tip of the iceberg. Everything else that we study in high school is pretty much all that stuff that's underneath the surface that we don't even know is really there. Now, we don't call these as undefined terms because we don't have a way of defining them. We call them undefined terms because they're more of an abstract concept that we use to develop all of our other defined terms throughout the rest of geometry. A point, generally speaking, is just going to be used to represent where something is. We name it with a single capital letter, and we just generally say, here's a dot with a letter next to it, and there's a point. A line, oftentimes you can think of a line as having one dimension, meaning that it can go left or right, it can go up or down, it can go front or back. It's just one way that it can travel. We often think of lines as just a collection of an infinite number of points that extends in opposite directions forever. It's named with a single lowercase letter, or any 2 points along the line can be used to name it. And I just kind of want to illustrate here. Let me pick a darker color now. Like this right here, that is the symbol for a line where, and I didn't draw that one very well. It's a horizontal line that has arrows on opposite sides of it. So there we go. Any 2 points name a line. Now, one of the things that I include here, here or here, or wherever you want to put it, we only use 2 points to name a line. Inevitably, students might see something like this where we have an A, a B, and a C all on the same line, and students will want to name that line A, B, C, and that is not a valid way of naming a line. We only use 2 points only, and the order that we name them really doesn't matter. So a plane doesn't have any thickness, width, or depth, but we often will refer to a plane as a 2-dimensional surface or a 2-dimensional shape. Because just like the board that I'm writing on, I can go up or down, I can go side to side, meaning that I can travel in 2 directions, therefore it's 2-dimensional. We name it with a single capital letter that's usually italicized, or any 3 non-collinear points And non-collinear simply means not on the same line. Not on the same line. So that's how those are our three undefined terms. That's how we name them. That's how we, generally kind of describe them. This parallelogram kind of looking shape for the plane, uh, that's a very typical way that geometry people kind of represent a plane, but it really is any three non-collinear points. It doesn't have to be in the shape of a parallelogram to be considered a plane. So as you're watching the video, kind of following along in your notes or just following along with the video, at this point it's asking you can you come up with some examples of points, lines, and planes that, in the real world, what would be a point, what would be a line, and so on. So if you need to, go ahead and pause the video now and answer these three questions. Come up with the examples that you need, and when you're done, hit play and compare your answers and with my answers and see what you think about them. All right, so I'm just going to assume that you've done the pause the video and answer the questions here. Three real-world situations that describe a point. I said a star, a city on a map, or a bullseye. Line, I said a straw, mop pad on a flagpole. And a plane, I said a floor, a piece of paper, and a soccer field. And those are by far not the only examples that we could use, but now moving on. So as I explained earlier in the video, there's only three undefined terms in all of geometry. It's a point, a line, and a plane. And everything else in geometry is going to be classified as a defined term, meaning it's going to have some general information about it, but then it's going to have some very specific characteristics about it. And the example that we see here is the word space. It's a set of all points that's boundless and three-dimensional. Well, a set of all points is just kind of the general information. But what makes it very specific is the fact that we're saying it's boundless in three dimensions. And we do this all the time when we're naming things. Like, just think about a dog. There's lots and lots of different dogs, and you can look at a dog and you say, hey, that's a dog. I know a dog when I see it. But what separates a German Shepherd from, say, a Golden Retriever? They have very specific attributes about them. Maybe it's the way their hair is, maybe it's the way their head is structured, the nose or something. But we have some very specific things that kind of classify it as being, well, this is what separates it from anything else. So moving on to the next part, these are some general vocabulary terms that we introduced at the beginning of geometry, where we're talking about how we make a definition. So the first one, set of all points boundless in three dimensions, that's space. We already saw that one. The next one, the set of all points, general stuff, that lie on the same line, specific, are collinear. Anything that's not on the same line would be non-collinear. Points or lines are on the same plane are called coplanar. Points, anything that's not on the same plane is non-coplanar. Now the last two are the ones that are my favorite that I always like to, mess with kids in class about, as far as, when you read those definitions, they both sound very similar to each other. However, the difference is that one is non-coplanar and one is coplanar. Because the general definition that we see here, when we think of lines that don't intersect, we generally think of parallel lines. Now the difference is that we have two types of lines that don't intersect. The types of lines that don't intersect but are coplanar are what we think of as parallel lines. The other non-intersecting lines are what we call skew lines. Let me just kind of draw a picture of what that might look like. If I have kind of a cube here, okay, and let's take red. If I say this line here and this line here, generally we would think of those as being parallel to each other because they don't intersect. And the difference is that they're coplanar, meaning that they make a flat surface between them. So if I connect the dots between the 4 points that make up the lines, we get a flat surface, meaning that they're coplanar. That's what makes them parallel. If, let's say I take this diagonal here in green and I take this diagonal here in green, neither one of those are going to intersect, but if I try to connect the 4 points, like this point here and this point here, you can see we don't have a flat surface anymore. We have something that's kind of twisted inside of the figure. So the diagonal line here and the diagonal line here, they never intersect, but they also don't create a flat surface if I try to connect the 4 points. So that's what makes it different from parallel lines, and we call it skew. Here, the way that what we're looking at this point are how the undefined terms interact with each other. If I have 2 lines intersecting each other, they intersect at a point. If I have 2 planes intersecting each other, they intersect and create a line. And if I have a line and a plane intersecting, they intersect at a point. It's a very common thing that geometry curriculums and teachers and authors ask about, so you might want to pay attention to that. Now at this point here, again, this is where I'm going to ask you guys to kind of pause the video and answer these questions on your own and see what you come up with, and from there come back and hit play and compare what your answers and your thinking is compared to mine. So go ahead and pause the video now, answer these questions. When you're done, hit play again. Okay, so hopefully we have our good answers here. How many lines can you draw through point A? The typical answer that I see in class when I do this with is the number 2, because students are going to say I can draw 2 lines using point A that look like that. But the question is not asking how many lines can I draw through point A that also include point C or B. It says how many lines can I draw through point A. So I could draw a line here, 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 and so on. So there's an infinite number of lines that I could draw through point A. Moving on to the second one, how many lines can I draw through B and C? And the difference between how question 1 is asked and how question 2 is asked is the inclusion of the word and. They're saying B and C. And in that case, there's only one line that contains both points, B and C, at the same time. Then it says draw and label a point D between B and C. So there's D. Just as how many different ways could you name it. In this case, there's 6. Any 2 points, name it in any order. So that's how we come up with 6 ways to name the line. Again, here I want you to go ahead and try and answering these next 3 questions on your own. When you're ready, hit play again and see how your answers compare to mine. Okay, so hopefully we have our good answers here. Give 3 ways to name the line. Any 3 ways, so if we're just saying we have some line connecting these things here, how would we name it? Well, there's just 3 examples. Remember, any 2 points on the line, name it, and the order of those points really don't matter. Here, there's a special note that I want you to take a note. I'm going to add some stuff here. 3 non-collinear points. I want you guys to understand, if I have 3 non-collinear points, 3 non-collinear points always make a plane. Any 3 non-collinear points always make a plane. So here in this case, we're talking about if we look at the lines that we can connect between those points, there's 3 lines there, and it says, can you name them? And I've just named them A, B, B, C, and C, A. So the last one, list all the possible names for the line and the plane. Well, I'm not going to name all of them because I don't have that much time, but if I wanted to name them, so these are just examples of how I could name them. Remember, any 2 points, name the plane, name the line, and any 3 non-collinear points, name the plane. So there's just some examples of how you could name these. Now, moving on from this point on, this is where the second part of the video is going to be coming into play. This is where students, if you have the handout, I want you to answer the next 3 pages of this handout by yourselves before you watch the follow-up video that will come after this one. So if you have any questions about what you've seen so far, by all means let me know, and I will be happy to help you out with it. But until next time, ladies and gentlemen, thank you for watching, and take care, and we'll see you soon.